Let's get rid of the beeps. Okay, stop beeps, mute all. Okay, welcome to Tuesday, and we're going to be talking about stellar explosions. Let me refresh your memory of where we are today. Okay, so we just finished the exam. We're on lecture 14. For the next 3 lectures, we're going to be talking about fun stuff. That's death of stars, star explosions, general relativity, black holes, all that good stuff. And then remember, this course is stars and galaxies. So we did the preliminaries. The next 3 lectures will finish up on stars, mostly the really fun and exciting things about stars. And then the next few lectures will be about galaxies. And then we'll have exam 3, which I know you're all looking forward to. So let's get started. We've got a lot of material. I'll try and cover this in 60 minutes, so we'll have time for questions. There'll be a lot of polls, and we'll move pretty quickly. Stay alert, because there's not much math here. In fact, I don't think there's any math, but there's a lot of detail, and it's confusing detail. It's easy to confuse nova and supernova. It's easy to confuse type 1 and type 2 supernova, and it's easy to confuse the various types. And it's important for your education and also for the exam to understand the distinction between all the ways that stars die. And unlike humans, where we just kind of lie down and stop moving, stars do not lie down and stop moving. Every star does something exciting and explosive towards the end of its life. Imagine if humans were that way. That would be interesting. Okay, let's get rid of that. Oops, shoot. Let's get rid of that. Plain window. Oops, here. Yeah, that didn't work. Okay, stellar death. So today we'll be talking about a bunch of topics. Like I said, we got a lot to cover, so I'll be going rapidly. We'll review the evolution of the sun, talk about white dwarfs, which is the end product of essentially all small stars. Then we'll talk about 3 types of explosions: nova, supernova type 1, supernova type 2. The 4th type of explosion is called kilonova. We're going to be dealing with that in a future lecture. It's a special type of explosion that we only first observed in 2017. So nova, type 1 supernova, type 2 supernova, and then we'll finish with a stellar death diagram. If we have time, I'll go over some videos where we show what happens if a supernova explodes near the Earth. It's not pretty. Okay. Remember the evolution of the sun. Here in the center is the evolution of the sun. We start with what we call a protostar, where a gas cloud will collapse and produce, once we reach 10 million degrees in the core of the sun, core of the protostar becomes a star. A star is born. Then it spends 5 to 10 billion years on the main sequence, doing nothing but watching TV, drinking beer, and eating pizza. And then it starts to blow up. And this happens when the core reaches such a hot temperature that helium starts to fuse. It produces a lot more energy, and it puffs up into a giant star, and then a red supergiant. It blows off its outer shells in a planetary nebula. And then it starts to cool down. And when it cools below 10 million degrees, the nuclear reactions turn off, and what we're left with is a white dwarf, which is the leftover core of that star, and it's tiny. It's the size of the Earth. We'll be talking today about what happens if you're a much larger star. And notice, if you're a much smaller star, you kind of go directly into the white dwarf phase. But this will take a very, very long time. In fact, longer than the universe has been around. So here are the 4 types of explosions, of which 3 we'll be covering today. A nova, type 1 supernova, and type 2 supernova. We'll go over the details in great detail. Sorry. A nova, it does require a binary system. Remember, most stars in the we haven't covered that. Most stars in the galaxy are married. There's at least 2 stars in the system. We're unusual in that there's only a single star in our system. There's only a single star in our system. And novas will blow up a lot. And this power is how many times a solar luminosity. So a nova will be 1,000,000 times the brightness of the sun. So if you're close to a nova, that's not a good day. And this is the description. We're going over this in detail. Type 1 and type 2 supernova, one of them requires a binary system, one of them does not. Both of them are billions of times the brightness of our sun. Typically, when a supernova goes up, it's brighter than the entire galaxy. You do not want to be close to a supernova. It would be the end of your planet. And then a kilonova is where 2 neutron stars merge, and we'll be talking about that in a future lecture. So let's start with a quiz. What's the most important property of a star that determines how it will evolve and die? We did this. We had this the last lecture. So this is lecture 14. Launch poll. Okay. Five, four, three, two, one. And that's exactly correct. Mass is everything when it comes to stars. Mass will tell you how long it will take you to be born. Mass will tell you how long, what your temperature, your surface temperature is. What is your luminosity? Mass will tell you how long you stay on the main sequence, and mass will tell you how you die. Mass is everything. Okay. Discussion question. How a star evolves depends on its mass. Why? So please put your guesses in the chat, if you would, please. Yeah, don't type all at once. It's hard for me to parse it when I see 20, 30 or 40 responses all simultaneously. Yeah, so we have for Matt, it says density. That's part of it. Mass determines how much fuel a star has. Hope that's exactly right. It's not the sole answer, but it's certainly part of the answer, that the bigger the mass, the more stuff you have to burn. Mass determines fusion. Yes. So Davis, you have it, you got a close answer. The real answer is that the more massive the star is, then the more pressure, the more density, and the more temperature there is at the core. And the hotter the temperature, the more the different fusion reactions that you can create. And the hotter it is, the faster those fusion reactions will go on. And so when you have a massive star, it's extremely hot. You have very complex thermonuclear reactions going on that produce lots of chemicals. And also they're happening very fast because you have very high density, pressure, and density. Mass determines density, temperature, and thus ability to perform nuclear fusion with heavier elements. Joseph, that's exactly right. Taylor, you're correct. And Quentin, you've kind of nailed it. And so that's just it. Okay. Why do massive stars fuse heavier elements than low mass stars? I already told you the answer, so let's see if you were listening. Let's see. I want to bring up polling. Huh. Five, four, three, two, one. And that's correct. Their cores are hotter and denser, and so it's easier for them to produce heavier elements, and it's easier for them to boost those heavier elements a lot faster. The fusion rate goes up incredibly fast with temperature and density and pressure. Okay. So that was we talked about evolution of the sun. Here is the future evolution of the sun This is should be refresher. We've got the core here of helium ash that was burned when the hydrogen was fused to helium, and that helium core then heats up until that helium core reaches 100 million degrees, and we have helium fusion. Core converts to helium. The hydrogen burns in a shell. The helium core and hydrogen burning shell produce more energy. And as the shell gets bigger and bigger, it's going to burn more and more hydrogen, and which means the luminosity will go up. And because the luminosity is going up, the radiation pressure of all of that energy will increase above and beyond the gravitational force trying to keep it together, and the star will puff up and become a red giant. And that will especially be true when we reach 100 million degrees and the helium starts to fuse. So here's what's going to happen with our particular sun. The star, over the next few 100 million years, our star is going to slowly increase in luminosity and size. Over the last 5 billion years, our sun has increased its luminosity by 30%. This is, of course, about astronomy, not biology, but it is just frankly beyond belief that our ecosystem has been able to maintain stability over the increasing solar luminosity over 30%. If you look at Venus and you look at Mars, both of those planets were habitable at one point, and they're no longer habitable because of very small differences in their relationship with the sun. So over 100 million to 1 billion years, the temperature of the Earth will increase another 10%, and that will reach the tipping point. When that happens, the Earth will no longer be habitable. So most people think we're looking at about 400 to 500 million years. So in 500 million years, the Earth will no longer be habitable. In 5 billion years, our sun will puff up to become a red giant. And when it does so, the Earth will be completely destroyed. The sun's radius will extend beyond the orbit of the Earth. Okay. Then the outer reaches of the sun will blow off into a planetary nebula. In other words, the sun will be so puffed up as a red supergiant, it can no longer keep control of the atmosphere that's at the outer reaches, and it will puff up and form a cloud. So here is the life cycle. We're here now. In 5 billion years, it will blow up as a red giant. It will puff up most of that, and then it will die as a white dwarf. Okay. So here's the sun as a red giant. There's Earth's orbit right there. And this will show you what it's like from outer space. Over 5 billion years, the sun will continue to expand and expand and expand. And as it expands, the surface temperature drops, but the total luminosity goes up by a factor of 1,000,000. I love this one.
This is an animation of the death of the Sun from the close-up viewpoint of planet Earth. The evolution of our main sequence Sun to its red giant stage would cause the daytime sky to change dramatically. Earth itself would also greatly change. The oceans would boil, the atmosphere escape, the land would burn, and life would end.
I love that. And life would end. Isn't that jolly? So when that happens, now, presumably we would have developed spaceships and we would have been long gone by then. So you might want to start packing now. As the red giant puffs up, it blows up those outer reaches of the planet. And this happens to all low mass stars. All low mass stars will puff up to be red giants and will produce these planetary nebulae. Now, the really low mass stars will do it, but it's going to take trillions of years, not billions of years. And we see these planetary nebula all over the place. Now, the word planetary is misleading. They were called planetary nebula because back in the 16th to 17th century, when astronomers were first looking through telescopes, they saw these fuzzy patches, and their telescopes at that time were so poor that whenever they saw a fuzzy patch, they assumed it was a planet. And so that's why they call these planetary nebula, although they have absolutely nothing to do with planets. They're just big balls of gas and dust that are the vestiges of stars that have died. Here's one of the more famous planetary nebula. This is the Cat's Eye Nebula, I believe. Near the Helix Nebula. Here is a close-up view of that. Here's the star blowing off its outer reaches. So it's not strictly speaking an explosion, because it happens over tens to hundreds of millions of years. But in this lecture, we're going to see lots of explosions. And our star will do exactly this. So that was a computer simulation, but now we're going to zoom in on a photograph. Okay. How will tardigrades fare? That's a really good question. You know, there are tardigrades on the surface of the moon right now. People are wondering if they're still alive. Okay, so here's the evolution of the sun. As we go, remember we covered this last time, I believe. It evolves into a giant, then the helium starts burning, it goes into a red giant, produces a planetary nebula, and eventually goes to a white dwarf. So let's show that with the simulation. So here is the a planet the size of our sun. Here's the size of it as it goes up, becomes a red giant. Then we have the helium flash, where that helium core reaches 100 million degrees, and it goes down, comes back up. The planetary nebula phase is over here, and then eventually it goes down and becomes a white dwarf, which is so small you can't even see it on this phrase. Just for completeness, let me show you the paths for other stars. Here's a smaller star. And here's the scale in mega years. So this is like 62 billion years. That's longer than the universe has been around. So this will take a very long time. Now let's get a really massive star. Let's go to 30 solar masses. Here, look at this. 5 million years, not billions of years, 5 million years. And it blows up into a supernova, produces a black hole, which we'll be covering in a little bit. Okay. So let's go back to the presentation. Okay. So that's what happens to our sun. So again, interstellar cloud collapses, produces the protostar, which produces the sun, which sits there for 10 billion years on the main sequence doing nothing. When the core starts, increases its temperature and pressure enormously. So the hydrogen to helium fusion takes off, produces a lot of luminosity. It goes up, produces a red giant. And then the helium core reaches 100 million degrees, and the helium starts burning to carbon and oxygen, and produces a red supergiant. And then it's so hot and so big that it sloughs off the outer atmosphere, produces a planetary nebula, and then the core eventually cools down into a white dwarf. And this happens to all low mass sequence stars.
A plot of luminosity and temperature allows us to follow the evolution of a one solar mass star from birth to death. Motion of the small white data point on the plot is roughly proportional to the time spent by the star at each stage. All stars spend most of their lifetime on the main sequence. Only late in life do they change into red giants, and after that, white dwarfs.
Okay. So we've talked about white dwarfs. Let's talk a little bit more about white dwarfs. White dwarfs are the end game for stars. We call them stars, but they're actually not stars because there's no nuclear reactions happening in them. That's because they're the cool ash. Once they drop, the temperature of that core drops below 100 million degrees and then 10 million degrees. There's nothing left to burn. And so typically white dwarfs are the leftover core In the case of our star, it's going to be mostly carbon, because the last nuclear reaction that happens in our star is where helium burns to carbon when we reach that 10 million degrees. The ignition for carbon is 600 million degrees, and our star never reaches that. It just isn't big enough. So we call these white dwarfs because they're very small, they're very compact. And what happens is, because there's no reactions going on, there's no luminosity to try and puff up the star. And so all that's left to stop gravity from shrinking it to nothing is what's called degeneracy pressure. Degeneracy pressure is a difficult concept, even for physicists. It's really that you might think of degeneracy pressure as you're in a room with fellow students, and it's impossible for two students to occupy the same place at the same time. You try and push and smash two students together, and you never can, because two students don't like to occupy the same place at the same time. And the same thing is true for electrons and atoms in a degenerate dwarf. What keeps the star from compressing is the fact that as you try and compress two atoms and two electrons together towards each other, they don't want to overlap, and when they try and overlap, they start jiggling. And it's called degeneracy pressure because it's a quantum mechanical effect, which is way, way beyond the scope of this course. So electrons are forced to occupy all levels. They're held up by the Pauli exclusion principle. Basically, electrons cannot be in the same energy level at the same location. Okay. 1 teaspoon of white dwarf material weighs 11 tons, about the weight of an elephant. Okay. So 1 teaspoon weighs 11 tons, and this is called degenerate matter. There's no such thing as degenerate matter on the Earth. In fact, there's no such thing as degenerate matter anywhere in our solar system, other than in, a few atoms in a particle accelerator. But it's not something that you'll discover walking around your house. And a white dwarf is about the size of the Earth. And remember, the Earth is 1/100th the radius of the sun, 1/1,000,000th the volume. And so here is the Earth, here is the sun, and here's a white dwarf in scale. And the white dwarf and the sun weigh about the same. A white dwarf is about 1 solar mass. Okay, so most of the mass of that star stays in this incredibly small, dense core. And it's called white because even though it's really small, it's the surface temperature is still at 5,000-6,000 degrees. The core temperature is less than 1,000,000 degrees. The surface temperature is white hot, as they say. But notice, because it is so tiny, the luminosity is way down. So that's a white dwarf, and white dwarfs are incredibly common because they're the end point of all low mass stars. If the Earth somehow moved close enough to a white dwarf, could it sustain life? Alex, that is a very active question in exobiology right now, because it certainly has the right luminosity temperature. And the question is, if there was a planet very, very close to the white dwarf, could it sustain life? And there's lots of positives, because you don't have a high radiation flux. The white dwarf isn't going to have big solar flares like active stars do. The only problem is that the white dwarf is the end game of stellar death. And in stellar death, it puffs up to a red giant and destroys all of the existing planets in that solar system. And so if there is a rocky planet close enough to the white dwarf to have life-sustaining luminosity, it would have to be very close to the white dwarf, and it could not have been an original planet, or certainly it would have had to been placed there somehow. And so that's the problem. The problem isn't, could you sustain life around a white dwarf? The problem is, how do you get a planet there? Because the progenitor star would have destroyed everything on the way to becoming a white dwarf. So now we're talking about nova. A nova is, we've observed these for hundreds of years, and for the longest time we didn't know what was going on. Nova is the Greek term for or Latin term, I'm sorry, for new star. We now know exactly what's going on. We know that in a nova, novas always happen in binary star systems. A binary star system, which we have two stars, binary. One of those stars is a white dwarf. The other one is a variety of things. It's usually just like a nice normal star. And so one of the stars has gone down that rocky path to stellar death sooner than its companion. It's like a, May, December romance sort of thing. And if those companion stars are really close to each other, then the white dwarf is so close to the companion, the white dwarf will actually suck material off of the surface of its companion star. Okay. It's called a Roche-Loeb overflow, but you're not going to be responsible for that term. So anyway, you're so close to the companion star, you're sucking material off of that surface. And when that material hits the surface of the white dwarf, and remember that white dwarf on this scale would just be a dot. Okay, you couldn't even see it. When it hits that surface, it will produce bright light. Okay, but that's not the nova. Here's the nova. The nova is when this material, and remember the core of the white dwarf is carbon for the most part, but the material that it's accreting onto the surface is hydrogen, because that's what the normal star is mostly made of, hydrogen. And when that hydrogen, enough hydrogen accumulates on the surface that the temperature of the hydrogen on the surface reaches 10 million degrees, it will ignite. It will ignite in what we call a nova, and it will produce a bright flash, a very bright flash that happens over several days, as you can see here by that.
Transfer between many binary star systems. An accretion disk forms when gas from a red dwarf star is pulled towards a companion white dwarf. When the disk overloads, matter builds up on the surface of the white dwarf and ignites, blowing off hot gas. Such nova outbursts recur periodically as the disk becomes reestablished many times.
Yeah, so the question from Matthew is why does the companion star not get blown apart? Um, it, Believe it or not, although it's a million times the solar luminosity, for the most part, it's mostly just radiation, and that radiation really isn't strong enough to move the orbit or disrupt the orbit in any way. And we know this for a fact because we see these nova reoccurring over and over again, sometimes recurring over a time period of just a few months. And so, no, these nova explosions do not disrupt the system. That's not true with supernova explosions. We'll be talking about that in just a minute. Okay, so this is a nova, which is a white dwarf very close to a companion binary star, sucking material from the binary star. And when the surface hydrogen reaches 10 million degrees, it ignites. The surface hydrogen explodes in a thermonuclear runaway. That's it. The white dwarf itself survives. The companion survives. We just see that bright flash. Okay. Let's skip this because we're going to be short of time in this course. Okay. So that was a nova. Let's talk about type 1 supernova. So it's actually called a type 1A. You won't be responsible for type 1A and type 1B. 1B is a weird thing. So supernova type 1A, it's also known as a carbon detonation supernova. These terms are synonym. Type 1 and carbon detonation are considered synonyms. So you are responsible for both terms. And what is that? Well, let's first go back to a guy called Professor Chandrasekhar. He was at the University of Chicago for years. He cut a pretty wide swath. Because he was Indian and he was went to Cambridge in 1930 at the age of 20, unschooled. He had this brilliant insight on taking the boat to Cambridge that really revolutionized astronomy, revolutionized physics, actually. And here's what he said. He truly understood degenerate matter, which at the time was extremely exotic. Many physicists at the time didn't even think it existed. And what he thought about was that degenerate matter can only withstand gravity up to a point, that there was a limit to how much force degenerate matter could sustain. And what he said was, when you reach about 1.4 solar masses in the white dwarf, 1.4 solar masses, that gravity will win over that degeneracy pressure, that the two students actually will occupy the same place at the same time. And I think both students in that case would be very unhappy with that case. And that limit, which is still true today, is called the Chandrasekhar limit. It's actually 1.44 solar masses. It's one of the most fundamental limits of all astronomy. So anything that is more massive than 1.44 solar masses and is made of and isn't in a thermonuclear reaction, in other words, it's just sitting there like a dead fish, it cannot exist over the 1.44, and it will collapse. He didn't say what it collapsed to, and we'll be getting into that in a minute. Okay, but he said it just cannot exist. And of course, because he was an Indian student, he didn't even have his PhD. Nobody believed him, but turns out he was right. And he became a very, very famous professor at University of Chicago, where literally no one, absolutely no one, has ever seen him without his suit and tie. And the big breakthrough when you got your PhD, if you were one of his students, was that before, when you were a student, he was Professor Chandrasekhar. After you got your PhD, you were allowed to call him Chandra. Okay, so the white dwarf's mass, if the white dwarf's mass exceeds 1.4 solar masses, then gravity wins. So how does a white dwarf increase its mass after it's been born? And, after it's the end result of that, it increases its mass by accreting material from a companion. So as the white dwarf continues this nova sequence, not all of the matter is blown off of its surface. Some of that matter stays. Okay. And as that stuff continues to accumulate, when you reach 1.4 solar masses, all heck breaks loose and it explodes. And what happens when it reaches 1.4 solar masses is the white dwarf begins to collapse. As it begins to collapse, its temperature and pressure and density increase. And when that temperature reaches 600 million degrees, which is the ignition temperature for carbon, then all of the carbon in the white dwarf ignites simultaneously. And this is unlike a star. A normal star, you have a thin shell of stuff that's burning hydrogen to helium. Here, the entire star ignites simultaneously. 1.4 solar masses simultaneously blows up, and you have a supernova that's brighter than an entire galaxy, brighter than galaxies that contains hundreds of millions of stars, hundreds of billions of stars. And in a supernova, the supernova explosion is so massive and so big that we believe that the companion is destroyed in that case. Okay. Alex, what if the Earth orbited a red dwarf? Would everybody be bathed in a red tinted light? So, Alex, yes, that's exactly right. In fact, there's a solar system that we'll be talking about briefly in the next to last lecture called TRAPPIST-1, where that's exactly that. There are planets orbiting TRAPPIST-1, a red dwarf, that are in the habitable zone, that have enough, that are close enough that the temperature sustains water at the surface, and we think it's a sustained life. But like you said, it's very red, and so your eyesight would be very different. So novas function like geysers. That is exactly right. Novas do function like geysers. They build stuff up and then they blow it up. How would the other sun be close enough to the white dwarf without? Okay, yeah, we already answered that. Okay, so this is the type 1 supernova. Binary star system. The stuff accretes it, and typically as it's accreting matter, you'll see a series of novas, but then when we reach the 1.4 solar masses, it explodes in a supernova. Okay. And when it explodes in a supernova, it does something interesting. It spews its guts through the universe. And here's the thing. In a star like ours, you reach some thermonuclear reaction, hydrogen to helium, helium to carbon. And that's pretty much it. So when our star spews out its atmosphere, we spew hydrogen, helium, carbon, some nitrogen, some oxygen, and that's about it. But remember, in this case, it is so massive and so hot and so dense that there are a lot of thermonuclear reactions that go on. And so when it blows up, it will spew all sorts of elements into the interstellar space. And these supernova explosions are why we exist, because it's these elements, the iron, the carbon, all of those elements, they can only be created in really massive stars or in these supernova explosions. And it's only through these explosions that those other elements are spewed through interstellar space, and those other elements then compress to form new stellar systems, such as ours, where they can form planets from that material that was created in the supernova explosions. Okay. So without explosions, without stellar death, we would not have us. We would not have biological life. Okay. Let's do this quick poll. Uh, so the increase in mass for type 1 must come from a companion star for this class of nova. Uh, Cole, I believe that's correct. We really can't think of any other mechanism for increasing the mass of a white dwarf. I mean, maybe if another star slashed into it, but the chances of that happening are so minuscule that for all the cases that we're familiar with, we've always observed the companion. Well, in cases where we've been able to observe the system before the explosion, there's always been a companion star. And that's exactly right. A white dwarf explodes when its mass exceeds the Chandrasekhar limit, the 1.44 solar masses. Okay. And yes, you are responsible for that. Okay, that's type 1 supernova, called carbon detonation, for the obvious case that it's when the carbon in the core detonates. Now we'll talk about type 2 supernova, which is more complex. Type 2 supernova, now the nova and the type 1 required a binary system. The type 2 supernova does not. The type 2 supernova happens uh, for an individual star. So here's a discussion question. Please put it in the chat. So Sam says, what if two run into each other? So Sam, yeah, that is a possibility, but the problem is the chance of that happening are infinitesimal. So remember, we are separated from our star by about 8 light minutes, but stars are separated from each other on the order of 10 light years, and a light year is about 10 to the 7th, about 10 million light seconds. And so stars are separated by millions to billions of times their own radii. And two stars running into each other, it just almost never happens. The only place it happens is at the center of our galaxy, where stars are incredibly dense. So, Joseph, that is exactly right. Iron is the most tightly bound element. Don't we observe two black holes colliding at one point? Yes, we do. How would that happen? The stars are so far away. So, Art, here's the thing: when we're going to be talking about black holes colliding in a future lecture, those are companion stars. Okay, those two black holes have been companions for their entire lives. So, and what happens is those companions then spiral into each other. So, in every case that we've observed black hole collisions, it's not naked single black holes running through space. It's two black holes that were born together, that lived together, and died together. Okay. Iron is the most stable nucleus. Fusing it won't produce any energy. That is exactly right. Okay. And this is kind of hard to follow, but we'll do it. Okay. So type 2 supernova. Now, in a very massive star, what happens is it's not hydrogen to helium and helium to carbon. It's hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to nitrogen, neon, neon to magnesium, magnesium to silicon, silicon to iron. Okay. And there's actually more shells than just what we're seeing here. Now, note again that the core is incredibly tiny. This is about the size of the Earth over a star that's 500 solar radii. So the Earth's orbit would be like about there. I mean, these stars are incredibly huge and they're incredibly dense. And they've got this really tight core where they've got all of these elements. And the reason why is that these cores are typically at billions of degrees, not millions of degrees. So you've got these incredibly intense and complex thermonuclear reactions going on, happening very quickly. Okay. So we have what we call an onion of burning shells, and each shell is burning faster. And this is way beyond the 600 million degree ignition temperature for carbon. And here is the graph that's hard to understand, but it's critical for everything we'll be talking about. It says mass per nuclear particle. What you can think of is that if you go from hydrogen to helium, helium weighs less than hydrogen. Helium weighs less than hydrogen. I mean per nuclei. And so when you go from hydrogen to helium, because helium weighs less, that mass is converted directly in energy. And so if you convert two hydrogen atoms into a single helium atom, that single helium atom will weigh less than those two hydrogen atoms. That mass is converted directly in energy. So as you go down slope in this graph, you generate energy. So carbon to oxygen, you're going down slope, you generate energy. Lithium to carbon, you're going down slope, you generate energy. So you can continue to go down slope. And this is called fusion, hydrogen to helium. You're fusing two smaller elements together to produce a larger element. That's called fusion. Now let's go down the street to the nuclear fission plants that power our lights. There, what you have is you've got big elements such as uranium, which has 238 nuclei. And if you fuse uranium to uranium elements, you don't gain energy, you lose energy. However, if you split uranium into, so for example, lead, you generate energy because the slope on this side of the curve is down. This is called fission. You generate energy by splitting atoms. Here you generate energy by fusing atoms. Fusing atoms, splitting atoms. As long as you go down slope, you will generate energy. What's the bottom of the graph? The bottom of the graph is iron. Okay. You can't fuse or fizz iron and generate any energy at all. So when you've gone to iron, you're at the end of the ball game. Iron can't do anything. Okay. Uh, so when you start to build up a significant amount of iron ash in the core, all sorts of bad things happen. Okay. And what happens is, as the temperature of the iron exceeds a certain temperature, and it's in several billion degrees, the pressure and the density is so great that the protons themselves start capturing electrons and turn into neutrons. Okay. And when that happens, the core collapses. There's no longer iron, there's no longer the degenerate pressure of the iron core to withstand the pressure. And in particular, some people think that when the iron core reaches the Chandrasekhar limit at 1.44, it collapses. And as it collapses, the temperature increases so much in that core that electrons combine with protons to form neutrons and neutrinos. The core shrinks, the entire star implodes. It all shrinks down towards the core, and when it reaches the tiny tiny core, then it will rebound in a shock wave, and that shock wave is then re-generated by all the neutrinos that were created when the protons were combined with the electrons to form neutrons. Okay. The mechanism of this actual collapse, and this collapse happens over milliseconds. The collapse, I mean, we talk about stars that live for billions of years, and the collapse of a star that forms a type 2 supernova happens over milliseconds. It's just enormously amazing. Modeling this in computers is something that people spend decades doing. One of the largest modeling groups is here at NC State, actually, trying to figure out exactly what happens in these supernova explosions, because it happens very quickly and there's lots and lots of complex stuff that happens. When the type 2 supernova happens and the core collapses, what happens is we go through the protostar, massive star, red giant, then it explodes. What's left over is either all of those neutrons, and those neutrons now form what's known as a neutron star, which is even denser than the white dwarf, or it forms a black hole.
Here we see the mass of a blue star at the top of the main sequence. When it explodes as a supernova, it creates a shell of hot gas that grows brightly in X-rays before the debris cools and disperses gradually into the interstellar medium. These X-rays reveal the dynamics of the explosion and the elements produced by the star.
As you can see, here's the onion structure. And the whole thing blows up and produces an incredible shock wave that permeates the galaxy. And as part of the shock wave, it's spewing all of its guts, all of those elements that it creates during the explosion. And the explosion is so energetic and so hot that even though it doesn't make any energetic sense, it produces elements above iron. Okay. So here is the type 1 supernova, the type 2 supernova. The type 1 supernova is a binary system. In a type 1 supernova, the entire star is completely destroyed. All of the carbon is ignited simultaneously. There's nothing left, sometimes not even the companion. In a type 2 supernova, the core collapse supernova, there is something left. And that something left is either all those neutrons forming what we call a neutron star, which we'll be talking about in a future lecture, or it forms a black hole. Why does it form one or the other? It turns out that there's a limit to degenerate matter called the Chandrasekhar limit, as we talked about. There's also a limit to neutron matter. And we believe, and this isn't quite as firm, we believe that a neutron star, which consists of nothing but neutrons, can exist that's larger than about 3 solar masses. And so if the core that's left over is more than 3 solar masses, it's going to create a black hole. A black hole is where nothing can stop gravity. Gravity continues to collapse stuff. And we'll be talking about black holes in great detail in the next lecture. So the remnant of the type 2 supernova is equal either a very dense neutron star or a black hole. So now let's talk about the stellar death diagram. So here is the sun. It goes up, produces a red supergiant, produces a planetary nebula, produces a white dwarf. A very massive star will go up to a supergiant, and all very massive stars will go type 2 supernova. Type 2 supernova produces a neutron star. Very, very massive stars, and we're not sure the exact limit, but we think it's about originally 25 solar masses, will go supernova and will leave a remnant core of at least 3 solar masses. And if it's at least 3 solar masses, it must produce a black hole. So the end result of low mass stars like ours is white dwarf. Intermediate mass, massive stars, but not incredibly massive, is a neutron star, and really, really massive stars is black holes. We've observed lots and lots of white dwarfs, millions of white dwarfs. We know of the location of a few thousand of these neutron stars and a few hundred of these black holes. So they do exist. We have observed them. Okay. So here is a diagram. Think about this diagram and where different you would put in different holes here. So a red giant with a small mass produces what would go in here. It produces a planetary nebula, leaving behind and just type it in chat, please. Something? White dwarf. That's right. You'll see white dwarf in a minute. Sorry about that. A red giant with a large mass will produce a type 2 supernova. This produces a white dwarf. A type 2 supernova will leave behind what? a neutron star, or black hole. That's correct. So a red giant that's small will produce a planetary nebula, leaving behind a white dwarf. If it's very massive, it will go a type 2 supernova and produce either a neutron star or black hole. And the next part of this diagram we haven't talked about in detail. Well, we have talked about this. A white dwarf with a companion will produce a nova, which goes back there, or a type 1a supernova, which just blows up. Okay. A neutron star with a companion, which we have not talked about, will produce X-rays. The X-rays come from material that, just like in the white dwarf with a companion, where material is streamed onto the surface, a neutron star with a companion, the material streams on the surface, but the neutron star is so small and so dense that when it hits the surface, it produces X-rays. And that's also true with black holes. Okay. So that diagram will be, you'll be showing this diagram over and over again, what happens with white dwarfs and neutron stars. We'll be coming back to that. So here we've covered these three types. We'll be covering kilonova later when we talk about neutron stars. Nova type 1, type 2, carbon detonation core collapse. Two of these require binaries. Do they repeat? Yes, no, no. The power, novas are 100,000 to a million, 4 billion for type 1 and type 2. A type 1 is the carbon detonation of the white dwarf as it exceeds the 1.4 solar masses, the Chandrasekhar limit. The core collapse is the iron core collapse of a supermassive star. Okay. And here is a diagram showing you the white dwarf, neutron star, and black hole. A white dwarf is the size of the Earth. Its density is 5 to 10 tons. There's 10 billion in our galaxy. Again, since every low mass star produces a white dwarf, they're hard to see because they're not very bright. They're hot, but not very bright. And so that's why we've only observed a few thousand of these. And the core must be under 1.4 solar masses, otherwise they would have blown up. And they're the end result of any star that's under 8 solar masses. So 99% of the stars in the galaxy will eventually produce a white dwarf. A neutron star, which is the end game for supernova, intermediate size supernovas, it's about the size of Raleigh. So on this scale, it would be infinitesimal. We know that there's hundreds of millions of those in the star. And the mass range of a neutron star is very tight. And we have never observed a neutron star that's outside this mass range. And if we did, then we know that all the physics we know is wrong. So all the neutron stars we have observed are between 1.4 solar masses and 3 solar masses. In other words, they're heavier than the Chandrasekhar limit, but they're not heavier than 3 solar masses. If they were less than 1.4 solar masses, they wouldn't have created a neutron star. They would have created a white dwarf. But if they're heavier than 3 solar masses, then they would collapse into a black hole. So if you put too much mass on a neutron star, just like you saw in a type 1 supernova, a neutron star would collapse to a black hole. We've never actually observed that. Chapel Hill, if we talk about, black hole, which we'll be talking about in a future lecture, it's about the size of Chapel Hill. Its density cannot be defined because it's a point. We know that there's millions of these in the galaxy. We've observed a few hundred of them, and its mass must exceed 3 solar masses by this definition. If we observed a black hole that was under 3 solar masses, that would be a game changer. We would know that there's things we don't know about the universe, which is not inconceivable. Okay. So last topic for today is death by supernova. What would happen if a nearby supernova went off? Okay. This is a nice diagram showing you the different layers. So if the nearby supernova happens, that's within 50 light years, it could kill many life forms on Earth through the gamma radiation and the high energy particles. And this would be kind of a 1-2 punch because the gamma radiation would happen instantaneously. In fact, it would happen simultaneous with the explosion. We would have no warning. The high energy particle would take some years to get here. And so we get this 1-2 punch. A lot of life would be destroyed with the gamma ray burst, but then the high energy particles would happen later and kind of do the finishing touches. We're in luck. There's no star within 50 light years that's big enough to go supernova. Imagine if there was. I mean, we would be a highly technological civilization knowing that there was an axe that could fall at any time. The most massive star known is 25,000 light years away. That said, there is a star about to go supernova that's relatively close to the Earth, and that's called Betelgeuse.
The cosmos can be a dangerous place for life. About every 50 years, a star explodes in our home galaxy, the Milky Way. These powerful eruptions are called supernovae. They can emit the same energy in a single instant that our sun will generate over 1 million years. Needless to say, if a supernova goes off close enough, life on Earth as we know it would perish. But just how close would one need to be? Astronomers estimate we have a comfort zone of about 50 light years. That's about 27 times the size of our solar system. Any supernova closer than that and, well, you get the idea. 50 light years may seem like a comfortable distance, but we're actually in more danger now than the past. Earth is currently moving through a peanut-shaped region of space called the local bubble. About 10 million years ago, astronomers think a neighborly cluster of stars went supernova, spewing their gaseous guts across the galaxy, which created the local bubble. Usually the local bubble is no cause for concern, but according to recent estimates, this residual gas could actually magnify the lethal effects of a supernova by increasing the amount of high-energy radiation that reaches Earth. The last time Earth felt the effects from a supernova was about 1.7 to 3.2 million years ago. The explosion took place 325 light years away. That's 6.5 times further than the danger zone, but Earth was still affected. Some iron from the star's core reached our planet. You can find it on the ocean floor today. There's no telling when the next nearby supernova will occur. But don't worry, at their brightest, supernovae can outshine an entire galaxy. So, at least we'll see the shock coming before it happens.
Yeah, there are several technical inaccuracies in that video. I like the video, but the thing is, we will see it coming before it happens. Well, that's true for the particles, but not for the gamma rays. The gamma rays happen instantaneously. But the thing is that some of the mass extinctions that happen on the Earth, there are many people who think that at least one of those extinctions was happened by a nearby supernova explosion. So supernovas, and we've been incredibly lucky that we've been able to survive the past supernova explosions. So what would happen if Betelgeuse went off? Betelgeuse is 750 light years away. So as distances go, it's close, but it's so here's the thing: that supernova will not. The Betelgeuse has been increasing and decreasing in its brightness weirdly for the past year, and so it will happen basically instantaneously. Of course, that could mean now, or it could be 100 years from now, or it could be 10,000 years from now. But on the timescale of that star, it's ready to blow up any day now. And here is the final slide I want to show you. These are the elements in the universe. Hydrogen and helium are formed in the initial creation of the universe. We'll be talking about that in a bit. Exploding massive stars, this green. Look at how many elements are created by these exploding massive stars. The blue are created in exploding white dwarfs. So those are type 1 supernovas. Dying low mass stars, these are the planetary nebula, okay? But without these supernova explosions, most of the elements that create life on Earth would not exist. And by the way, notice these really heavy elements are created in merging neutron stars. We'll be talking about that later. Okay, that's it for today. I'm opening it for questions. I see some questions here. infinite district theoretical, or because I can't comprehend that? So Matthew, I say infinite, I'm kind of joking that the thing with the black hole, it's like what happens in the black hole stays in the black hole. There's, by the way, you can turn your mics on if you want. There's really no way of knowing what happens inside the black hole. You can go in, but you can never come out. So we can never gather information about what happens inside the black hole. So we honestly do not know. Do the matter collapse to an infinitely dense point or not? We just don't know. And there's no way to find out because we'll never know what happens inside a black hole. Where's the guardian of the galaxy? Not a clue. What if the moon eclipsed the Betelgeuse supernova? That would be very interesting. I mean, interesting from an observational point of view. It wouldn't have any direct effect. Since it's 750 light years away, could have already blown up and we're just waiting for the light to reach us. That's exactly right, Art. And that's the weird thing about astronomy, because lots of stuff has happened, and until it reaches us, it hasn't happened. I mean, the universe could have done away with itself, and we won't know it until it finally reaches us. Dr. Katie Mack, who's co-teaches this course, wrote a book called The End of Everything. And she actually has one theory that what they call vacuum collapse, that the universe is collapsing. We just haven't found out yet. And when it does collapse, it will happen so fast we just don't know what happens. It's just blink, we're gone. Can we take a field trip to a black hole? I will be the sacrifice. I will watch. That's cute. So what would happen to the solar system if the sun turned into a supergiant? We will find out, because that is exactly what will happen. The sun will expand out to a red supergiant. It will swallow Mercury, it will swallow Mars, and it will swallow the Earth. It will not swallow Mars, will continue to orbit, but it will swallow those inner stars. And we believe that the other planets will continue to orbit, but they'll be much farther out. Why would 9 low mass stars be able to produce the higher mass elements if they stop fusion at helium fusion? Yeah, so that is a case. The issue here is that I've simplified things enormously, because although the main thermonuclear reactions that are going are hydrogen to helium, helium to carbon, there's a lot of these other fusion reactions that are going on at a much lower rate, at very low temperatures. I mean, low temperatures, relatively speaking, hundreds of millions of degrees, through other processes than what we've talking about. There's the P process, the S process. And the S process in particular, those studies are being done at University of North Carolina at Chapel Hill. There's experts in that process. And I don't talk about the S process here because it's not core to the discussing stellar death and stellar life. But there are what the thermonuclear, the nuclear reactions that happen in stars, even low mass stars, are very complicated. But you might notice that the stars that are listed in yellow are all extremely rare. Okay, very, very rare. I don't see a single element on there, with a possible exception of Mercury and lead, that there's a lot of. Okay, so we're talking about very, very minor components. Other questions? And again, we ask that you have at least, 5, you have questions in at least 5 lectures. I'll answer questions. Well, I'll certainly try to do the best to answer questions on any topic at this point. By the way, you all did very well in the exam, as I would expect. What if 2 companion stars both form white dwarfs? Is there a reason that can't happen? There's absolutely no reason that can't happen. And people have been looking for, binary systems consisting of 2 white dwarfs. We don't think that anything would happen past that point. They would just continue to circle each other. And because the luminosity of those 2 white dwarfs is very small, they would be very difficult to see, but not impossible. And so I think people have looked for that. In fact, let me see if anybody's ever found one. Binary white dwarf system. Good question. Other questions? Do you have any experience with strange quark matter? No. Yeah, there are people that postulate that there exist neutron stars made of strange matter, and I never studied particle physics, so I really don't know, other than the fact that it's really strange stuff. Brody, if you haven't chosen a topic for your project, you should choose that. Okay. Other questions? Okay. If there's no other questions, I'll end it here, and I will see you all on Thursday. You also invent software. Actually, that's true. I started 2 software companies. I started working in in fact, I wrote the world's first interactive flight simulator in the 1970s. I started a software company called Spyglass, which was responsible for the world's first web browser. Um, and then I started a second company that did scientific visualization software. So yeah, in fact, I went back from software back to physics. You want to harm me as an intern this summer? My offers have been dry. Yeah, people keep asking me to start another company. I've done 2. One was wildly successful. One kind of crashed and burned, and I don't know if I have a third company in me. So, yeah. Well, thank you, Brody, for saying brand for president. I got to tell you, I will be for anybody who believes that there is an objective truth in the world that is independent of politics. And when I see facts and science and reality trashed every day, it, it I burn with the red hot flame of a supernova explosion. The world does exist as independent reality, independent of your politics. And we should fight over what that means, but we shouldn't fight over the concept of reality. We shouldn't fight over the concept that facts are facts and science is science and truth is truth. So anyway, other comments? Thank you so much. I'll see you on Thursday. It's been fun. Bye bye.